All right, so let's talk about weight. Weight and weightlessness. Force of gravity, like anything, any other force, causes acceleration. And, you know, when you're under the influence of gravity, you're being pulled toward the other object and you're being accelerated in that thing. Now, we're usually in contact with the Earth, and so we think of gravity as something that presses us against the Earth rather than as something that accelerates us. But technically, you know, gravity is an acceleration, or that force causes acceleration. But we feel that force pushing us on the Earth. All right. Now, let's say that you stand on a bathroom scale, and if you do that, what that scale reads is the force of attraction between you and the Earth. Okay, that's what it's going to read. If it says by Newton's third law, the floor and the scale in turn push upward on you. So you're pushing down on the scale's pushing up on you, and that's how we measure that particular thing. Those forces compress the gauge, and that's the weight that we think about when we look at a scale. Now, if you try this in an elevator, you're going to find that your weight varies. So if you're in an elevator, and here you are, and you stand on a scale, and that elevator moves up, you now have even more acceleration pushing you down. So that scale reading is going to increase. Or if you're opposite, if the elevator is going down fast, you're going to have less of a reading. It's going to be smaller on that. Okay. So if it accelerates downward, the support force of the floor is less, therefore your weight decreases. If the cable breaks, you're going to feel weightless. You're not going to have any force on that scale, at least for a short time. Then you'll feel weightless. Weight again, I guess, at the end. Okay, so here we are. Now, obviously, she didn't take into account the idea that she should jump right before the ground, before it hits, right? All right, so rather than define your weight as the force of gravity that acts on you, it is more practical for us to define weight as the force you exert against a supporting floor. So according to that definition, you're as heavy as you feel. And therefore, the idea of weightlessness is not really the absence of gravity, but the absence of a support force. So that's kind of what we were talking about. Even the astronauts out in space are not technically... there's what I say. There's not that there's no gravity. It's just that they have this feeling of weightlessness. But then so does this person who drives off the cliff. And I've noticed in physics there are a lot of people who drive off cliffs. So obviously I would not want to be making a physics book and demonstrating a lot of the things that they do. All right, let's talk about tides. All right. What happens with a tide is the fact that the moon's attraction is stronger on the Earth's oceans that's closer to the moon and weaker on the Earth's oceans that is farther from the moon. And that simple thing, because of the fact that the water can move pretty easily, this creates the tide. So it is simply the gravitational force is weaker with increased distance. So the farther away, the less force that we have on the tides. So the ocean tides are caused by differences in the gravitational pull of the moon on opposite sides of the Earth. Now, the difference in pulls along the Earth is slightly elongates it. So the oceans bulge out about a meter on both sides. And because the Earth spins once a day, if you're standing on a fixed point on the Earth, you'll pass under these bulges 2 times a day. Therefore, you get 2 high tides and 2 low tides. So what they're talking about is this. As the Earth is spinning, notice it's spinning this way. We're spinning through this. If I'm standing here, I'm noticing a high tide right here because the pull of the moon is greater here than it is on these other areas over here. So the moon is actually moving the ocean water higher at that point. And then as the Earth rotates, now let's say I'm halfway through here. Now this would be low tide when I'm here. And I get another half of the way or a quarter of the way. Here, I'm now at another high tide, and then on the back side, I'd have another low tide. So really, I always, you kind of think of the ocean as being pulled to the earth or whatever. I don't know. I always think the water's being pulled up onto the shore, but that's not really what it is. What it really is the ocean is kind of staying there, and the earth is kind of spinning underneath it a little bit more. The bulge is kind of staying there. Kind of think of it like the big wave. It's kind of stuck in one area, and the earth kind of rotates underneath that, and that's where we get high tides and low tides. There's also other factors that affect ocean tides. The sun, for instance, can affect them also. In fact, the sun is 180 times greater pull than the Earth's, but notice the sun doesn't make near as much difference on the tides as the moon does, because there's less difference. Let's see if I can find a picture here. All right, so here's my sun, and what they're saying is this pull on this part of it here compared to the difference of it being on there is not very great. There's not a lot of difference. Whereas with the moon, the difference from here to here is quite a bit more. So the moon has actually more effect on the tide than the sun does. But the sun does have some effect. And when these are lined up, this is what they're trying to show you here, when they are lined up so that we've got the Earth in the middle of the moon and the sun, when those are in a line, so either side here, when we've got lined up, then we get the strongest tides, the biggest tides. These are known as the spring tides, and those are higher than normal. And when they are, what happened here? Okay, whatever. And when they're at 90 degrees or perpendicular, those are known as neap tides. And that's when the tides are not quite as high as normal, because those forces kind of counteract each other. So here's an example of that. So here's the moon pulling here, the sun pulling here. Those tides tend to kind of counteract each other a little bit. And these would be when you have the smallest ones of these. These would happen when you have the strong tide, the spring tides. Those happen at new moons and full moons, and these tend to happen, in between, halfway between the new moon and the full moon, when we get that. Here's an interesting thing. There are other types of tides. We actually have earth tides. The earth itself actually moves. Now, we don't notice as much. It's not as pronounceable, but it does say that the solid surface rises and falls about 1/4 of a meter every day, twice each day. So, if you're just standing on the earth, standing on the grass, there's an actual difference. You're actually changing, depending on where you're at, might actually be a little bit higher or a little bit lower, depending on the rotation of the earth and the moon and the sun and all those things. And it also affects the atmosphere. There's those kind of things that go into that too. Now, because the earth is tilted, these high tides are not exactly the same. So, for instance, here's what they're trying to show you is, if I'm on this part of the earth, and when I'm on this side, hey, it's not quite as high as when I'm over here. Now I'm underwater, because notice that, this is where the moon is. I'm a lot closer to this line here than I am here. That's what they're trying to tell you. Now, if our axis, if this were up here and it went straight down, then it would be exactly the same on both sides. But because our earth is tilted on the axis, then it's not quite like that. So one tide during the day is even higher than the other high tide, I guess, is what they're telling you. Now, the moon does not usually produce tides in a lake. And the reason is because in a lake is a pretty small thing, and there's not much significant difference between that. So in other words, here's my lake, and here's my moon, and the difference from here to here and here to here isn't very much, versus the difference from here to here and from here to here is, notice how much longer that one is than the other. So that's why you don't see much tide in a lake. I don't know why it keeps wanting to do that. Okay.